Hello everyone. Welcome to a session with Anirban Chowdhury regarding quantum Hamiltonian complexity in thermal equilibrium. As the name implies, we're going to be focused on computational complexity in this session, particularly when it comes to describing systems that are in thermal equilibrium. With that, we can jump into the discussion. To give an introduction partially to yourself, but then also to this paper, would you mind just giving some background as to why you chose to write a paper on this particular subject and what your research focus is in general?
Right. So to speak about this paper, so broadly we were interested in this question of essentially how in terms of computation, how do we study quantum systems which are in some kind of something called thermal equilibrium. So thermal equilibrium is this kind of idea in physics where if you place some kind of object in some environment where it's exchanging energy or heat with its surroundings, it kind of reaches like an equilibrium state, which means that the temperatures of the two things, like it's at the same temperature as the environment, and no more further exchange is happening at a macroscopic level. So these are like systems you encounter every day in your life, right? So that's quite relevant. So if you have a cup of tea, it cools down, it reaches some kind of temperature. Now, in terms of physics, you want to understand, well, what are the properties things can have in this thermal equilibrium state? So if you have some kind of system that's built out of some particular kind of molecules and you want to engineer this in a lab, well, what kind of properties do they end up having? And is there some way to engineer these to have certain desirable features? These are some kind of like far applied questions you might be interested in. But to make those applications conceivable, you first need to understand what can happen. So that's the goal of this kind of broad goal, this kind of thing, where you have like something called quantum many-body systems. So now you have a huge number of quantum particles, and these are we supposed to be in some kind of thermal equilibrium. And what kind of states can they be in, and what can you say about their properties? So that's the physics question. Here we're interested in, okay, what is the computational complexity of this physics question? Suppose you have a quantum many-body system in thermal equilibrium, and you have some idea of its Hamiltonian. And a Hamiltonian is like a model of how the particles interact. That's like the rough idea of a Hamiltonian. So given some kind of Hamiltonian as an input to your problem, and the task being compute its thermal equilibrium properties, certain quantities, how difficult is it to compute those properties? And when can you have efficient algorithms? And when is it just out of the question to have anything that's efficient? So that's the kind of question we are addressing here. And now Hamiltonian complexity is kind of one of the main areas in quantum computation. And typically people have looked at this question of Hamiltonian complexity for something called ground state properties, which is again an equilibrium state, but it's a very low temperature state. Here we're interested in when things are closer to room temperature or some temperature above like something called absolute zero. So absolute zero is when you would get to the ground state. And for that, we have some kind of understanding as to how the computational complexity is, what happens. And we are, in this work, we are kind of trying to initiate the same study in the case of finite temperature or thermal equilibrium systems. Does that help?
Yes, absolutely. So a couple of follow-up questions on that. Sure. Maybe the first thing would be just when it comes to the term that you used, Hamiltonian complexity. When we're talking about Hamiltonian complexity in general, what are we exactly referring to then? So we have algorithms here with a particular complexity that we're assessing, and my understanding is that is mostly related to the free energy of these systems that are to some sense dictated by the Hamiltonian, but saying Hamiltonian complexity sort of sets the tone that this is something very intrinsically related to the Hamiltonian, like a specific problem. Could you shed some light, more light on what that means? Yeah.
Right. So as you correctly pointed out, in this case we are looking at the free energy or something closely related, the partition function. But Hamiltonian complexity just means that, in this case, everything about the problem is pretty much set by the Hamiltonian. The Hamiltonian is the description of the system that you're starting with. And from that, given the Hamiltonian, what is the complexity of the problems you formalize? Previously, people looked at ground state energies mostly, and here we're looking at the free energy or this partition function version of the problem. But Hamiltonian complexity is just the general name of the field. Like given the Hamiltonian, and now you ask a question about some physical properties of the system. How hard are these problems? How difficult are these in some computational sense? Are they NP hard, or can you solve them in polynomial time? And there are quantum versions of these. And things like that pretty much. And in this case, as you said, we're looking at the free energy. as the thing we want to compute.
Okay. One more question I would have is why we're looking at this in the thermal equilibrium state to begin with. So let me preempt that question a little bit more. So in the introduction, I believe you're stating that you're investigating the estimation of free energy for k local Hamiltonians, and we'll get into that in a second, that describe a system of n qubits with interactions among the subset of at most k qubits. Now, if we're talking about qubits in particular, or I'm assuming the applications of this are somehow intrinsically related to qubits, why are we considering that in a thermal equilibrium state?
So, just to go to one specific point, you said the applications may be intrinsic to qubits. I would say that's not necessarily correct. Qubits are in some sense abstractions that you use in your quantum computer. They are the analogs of bits. But using these qubits, you can model various different things. Like, in a computer, you can program some simulation of some real world property. So even with qubits, you can simulate something called fermions or bosons or things you might actually encounter in a lab. So the scope of this, the applications down the line, are quite broad. Qubits are in some sense are abstractions. And the point is just that qubits are what we'll have in some kind of programmable quantum computer. So given these qubits, we have access to these qubits, what can we model, what can we efficiently compute? And thermal equilibrium is interesting because it's something that just we encounter frequently, either in a lab or even in real life. Like systems in finite temperature, above a zero temperature, this is something you'll encounter quite often. And therefore, these are relevant for real-world properties of quantum materials. That's the main, I would say, the motivation for studying thermal equilibrium.
Okay, so if I understand you correctly, we're studying thermal equilibrium not necessarily because, like, if we're thinking about the architectures that this might potentially be applicable to, if you would have something like a superconducting architecture and you're actually trying to describe the qubits themselves, I suppose a thermal equilibrium state would not be representative of how those qubits interact to begin with. Are you saying that we're doing this to investigate what modeling a thermal equilibrium state with the help of a quantum computer, for example, would require? Or is it that we're looking at separate architectures altogether and therefore we want to model how qubits in a thermal equilibrium state would interact?
Right. So let's see. So this, I would say, is something that is more like kind of at a higher level than something you might think of at an architecture or device level. Now, when you talk about architecture, you're thinking about, okay, how do I build my quantum computer? And there, some of this physics, like thermal equilibrium, might go in, but that I would say is not directly relevant to this particular work. Here we are trying to think about something called many-body systems. Suppose you have a very large number of qubits put in some kind of quantum state. Then how do they behave? And that is not, it may be, but it's not directly relevant to the kind of engineering people might do in a lab where they're trying to build qubits out of some kind of material. So this, I would say, is more in the case, this would be more relevant to say, you're trying to, if you suppose you have like a large quantum computer, which has error correction, all these things built in, and you want to study other physical systems in this computer. You want to do some kind of quantum simulation of more complicated physical systems. Then in that kind of setting, the systems you might try to simulate, the properties of those are what we are trying to talk about here. So not directly the ones that people are building in the labs when they're building qubits, but something you might try to program onto them at some point, something like this.
Okay, understood.
Yeah.
So then maybe we can talk about some of the concepts that are introduced early in the paper. So we mentioned these already. We have the Helmholtz free energy that we have defined here, and then we also have the partition function up here.
Yep.
Would you mind describing what these two terms represent and why they're relevant for these kinds of investigations?
Right. So at a high level, I like to say that these quantities, the partition function and the free energy, they're kind of like master keys that unlock physics for thermal equilibrium systems. Okay. So if you have the ability to compute the partition function for a certain temperature and a certain Hamiltonian, or equivalently the free energy, if you can compute these quantities easily, then you can directly compute other properties of the relevant physical system. Okay. So it's like a general purpose tool. If you know how to do it, you can do many other things about the system. You can learn a lot of things about the system. So that's why these are interesting. So they're interesting from a physics point of view. When you're trying to build your theory as to how you can theoretically model your systems, theoretically understand them, these are very foundational quantities. And the partition function, going into a bit more detail, it is in some sense, it captures the details of energy statistics. So in a physical system, various configurations can have different energies. And if the system is in thermal equilibrium, it's exchanging some kind of energy with an environment. What happens is that the system occupies each of these energy states with some probability. Or if you have a large number of systems, some fraction of them occupy certain energy levels. And their distribution follows something called the Maxwell-Boltzmann distribution, which means that it roughly goes as exponential into times minus beta that you see here. So minus beta times the energy. Okay. So that's just that factor, this exponential factor, just dictates, well, what is the probability that your system will occupy a certain energy state? And the partition function is like the sum of all of these Maxwell-Boltzmann factors. And mathematically, this is interesting because you can compute other things from it once you can compute it.
Okay. And so the parameter in these functions would be beta in that case, or is beta held constant and then you just somehow change the Hamiltonian? If I'm thinking about these as
Sorry. So beta is something called the inverse temperature. So that's like 1 over some constant times the actual temperature. So this is like just a little relabeling of variables, because the like having 1 over temperature is kind of annoying to deal with. So you just talk about things directly in terms of beta, which we call the inverse temperature.
Okay. And so in these functions, if you would actually use them, you would use beta as your parameter in that case. And the Hamiltonian is fixed for a given system.
So the Hamiltonian is fixed for a given system. Beta, depending on the problem, it might also be given as an input, or you might be interested in computing this quantity for different values of beta. So sometimes we are interested in computing something called the phase diagram of the system, which means what are the different phases a certain matter can have, depending on some parameter, like the temperature here. So to compute the phase diagram, you would be interested in computing this free energy and the partition function for various different values of beta.
Okay, good. Maybe we can talk about the Hamiltonian then a little bit as well. So we have the Hamiltonian, as you mentioned, in the first expression here. Can you summarize the kind of Hamiltonian that you're considering, why you're considering that kind of Hamiltonian to begin with, and then we can dig into the different kinds of restrictions, let's say, in terms of scope that you made.
Right. So to begin with, we are dealing with something called k-local Hamiltonians. So these are Hamiltonians which are made up of like a bunch of simple terms. So you have each term is something like an interaction, and k-local means that this interaction is an interaction between k of the qubits. So recall again, the full system has n qubits, where n is some number, and we are taking k of these, and this k is a constant. It cannot scale with n. N can be like a variable, it can change, it can have different sizes, but k would be a constant regardless of that. So k-local just means that this is a Hamiltonian which made up of a bunch of simple interactions, and each simple interaction couples at most k of these particles at one time. And this is directly the analog, in some sense, of a problem in computer science called k-maxsat, where you have some kind of constraints which couple k of your variables, and you want to find some solution to your problem satisfying all of these constraints. So this is some terminology borrowed from more or less the computer science literature, where we talk about k-local Hamiltonians. So that's the basic Hamiltonian that we start with. And we have some like 3 different families of results. So most of these results hold for these k-local Hamiltonians, except this one subheading that we see here, this efficient algorithm for dense 2 local Hamiltonians. For these, this k is set to be 2. So each interaction couples at most 2 of these qubits at a time. And then we have something also called the density. And maybe we'll get to that later. But generally, k-local just means that a Hamiltonian made up of interactions, each interaction couples at most k number of particles, where k is a constant, independent of how large your system is.
Mm-hmm. And when we say that it couples at most k different objects, let's say, what kind of, do we have any restraints on what kind of coupling occurs between these?
At this point, I would say there are no restrictions as such. There could be any general quantum coupling. There are some. There's a constraint which is like, what is the maximum energy penalty of each of these constraints? So each constraint comes with some kind of like an energy cost, and we assume some kind of upper bound on this energy cost, because if you allow like infinite cost for each of this, the problem becomes obviously trivial things, kind of irrelevant things like that happen. So we assume some kind of upper bound.
Mm-hmm. Okay. if we start looking then maybe at the header that we mentioned before, so the efficient algorithm for the dense two local Hamiltonians. So now we have just two interactions then, and there is some analogy to this with some form of graph as well. Would you mind describing what that analogy would be for these kind of systems? Maybe that will give some additional intuition.
Right. So consider, like, suppose you have n particles and now you have two local interactions. So each interaction can couple two of these qubits. So we're talking about qubits here. But it could in principle couple any two qubits. Okay. So you could have like n choose two of these couplings. Now,
okay.
Your interaction graph is something that tells you, well, out of these n choose two couplings, which of these are actually there? So again, like if you could think of interactions as a graph, you could have like all of these qubits placed at the vertices of a graph, and there'd be an edge connecting all of them. Now, let's say you remove some small fraction of the edges. So again, you have a number of interactions that is not n choose 2, but something slightly smaller. And that would be the setting of a densely connected graph. So the graph is not a complete graph, which means that it has all the edges, but nevertheless, it has almost all the edges. And so any two vertices or any two qubits are kind of connected with high probability. So that would mean like a dense graph.
Mm-hmm. Okay. And what kind of systems would actually be, let's say, translatable to this kind of Hamiltonian? I guess this is potentially a generalization of systems, right? So I would expect that we don't necessarily have interactions between, if we're talking about qubits now that are far away from each other, like mostly I would assume those to be local as well.
Yep.
Nevertheless, what kind of systems are well represented by this kind of,
right.
approach?
You raise a good point, yeah. So dense systems are typically not something you might encounter very frequently, but in many cases you can approximate other systems with something that looks kind of dense. So if you have like a high number of spatial dimensions, then that could be close to being dense. If you think of something like perhaps like a gas, where particles can talk to each other over long distances, and particles can come close to each other and interact, that you might be able to model as a dense system. But other than that, I would say in terms of things that you might have in the lab, dense might not be directly translatable. But certainly there are systems you can reasonably approximate by modeling them as dense systems.
Mm-hmm. Okay, fair enough. So if we look then at the different approaches that you took, looking again at the dense two local Hamiltonians first, what's the reason for making that restriction in terms of the scope? How is that simplifying the problem more than considering the general case?
Right. So before I get to that question, I might say a few more words about why this dense case is interesting. So classically, for these kind of dense systems, we know that something called mean field theory works really well. Mean field is where you replace the interactions acting on each particle, and recall that one qubit can be interacting with a large number of other qubits. So we can replace this sum of these interactions with kind of like an average, and this lets us do a mean field approximation, and this often leads to good approximations. So there has been a lot of interest seeing whether this kind of idea translates into the dense case for quantum systems. And there was some earlier work which showed that this is indeed the case, up to some assumptions, for ground state problems. And here we're doing kind of the analog, again in a high level crude sense, for the free energy problem. So that's the kind of motivation, that dense systems are often easy to deal with, they're tractable. Now does that property carry over to the quantum case for this free energy or thermal equilibrium problem? And in this case, why the dense setup becomes easy? Well, it turns out that there are certain ideas in classical machine learning and classical computer science tackling such dense systems using a particular technique, and it seemed like it would be possible to translate these techniques to the quantum setting. That was how we started looking at this dense setup. Okay. So that's that how technique? So this is a family of some idea called convex relaxations. And this is the loose idea is that you can formulate such a free energy problem as a convex optimization problem. But it turns out that the basic formulation of this convex optimization requires optimizing over 2 raised to n by 2 raised to n matrices, exponential size matrices, because your quantum state it kind of grows exponentially with the number of particles. Now, but you can use this idea of convex relaxations, which says that you can get some kind of lower bound to the free energy, some kind of something that is below the free energy, by instead doing a relaxed optimization. So instead of optimizing over these large matrices, you optimize over some kind of smaller data structures, which in some sense capture local properties of these density matrices. And doing this gives you a lower bound. And now there are certain techniques which go by the name of so-called rounding techniques, which lets you rigorously bound how good this approximation is. So this is some idea that's been used in the classical computer science literature for looking for approximation algorithms for so-called constraint satisfaction problems such as SAT, MaxSAT, things like that. And we thought, okay, it looks like we can take these and port them over to the quantum setting with some more work.
Okay. Okay, I think I get it. So when I think about the algorithm and the structure associated with it then, like in the approach that you're taking now, you would then have a relaxation of the original problem. Also, I take it for this two-local Hamiltonian case, where you can reformulate your problem into a convex optimization problem. You would then solve that problem and get some solution out of it, and then the final solution is what you would then apply to this rounding algorithm and get sort of your final estimate for the local energy. Is that, or for the free energy? Is that right?
That's good. That's more or less right, except in the final stage, the rounding is not an algorithm you would actually do. The rounding is kind of like a proof technique. So you show that, okay, you have these like objects that look kind of locally like quantum states. These are things these are things you do the relaxed optimization over. You kind of keep like patches of quantum states which match up locally, and you run some optimization over them. So at the end, you get some answer, and corresponding to that, you get patches of quantum states. But the problem is that these small patches may not be consistent with the full quantum state assignment. So you don't quite know if your answer you got is actually correct. So the rounding is a process which says that given these kind of small patches of states as input, I can merge these together into some kind of full quantum state while changing these small patches only by a small amount, and therefore by changing the objective only by a small amount, which means that with the answer you got, it changes only very slightly if you go to a full state. And this kind of shows that even if you were to write down a full state, like a fully consistent state, the answer that you would get would match up quite well up to some approximation to the one that you got by doing this relaxed optimization. But you don't need to do this merging to get to the right answer. The thing you got from the relaxation is a perfectly fine answer. So this rounding is kind of like a proof. It does not quite appear in the algorithm. The algorithm is just saying, well, run this relaxed convex optimization.
Okay. Would it be when I'm not sure I understood the details of that. When you put these together with the rounding procedure, to me that sounded like you're reconstructing a state from the original smaller patches. That state somehow is probabilistic in nature because you have these different applications that you don't have full control over for the system. What I'm trying to get to is with that probabilistic nature, if that does exist, do you ever risk violating the original constraint that this approximation will be lower energy than the original one? Like, could you ever end up now in a reconstructed scenario where the final energy is actually higher than the approximation, or is that a firm bound, let's say, that the final energy would always be lower?
So let's see. So I might have to give a few more details. So the basic idea is this free energy. You can write it as the minimum of some quantity, some functional, over all density matrices. Okay? So it's like the minimum of a convex program. The relaxation gives you a lower bound to the free energy. But at this point, if you just do the relaxation, you don't know how far that lower bound is. So it's something that's below the minimum free energy. And the rounding lets you go from here to something above, okay? Because you go from like a set of not quite states to something which is a state, and it has a corresponding energy. So you go to something like over here, let's say. But you're guaranteed that this will be something above the minimum of the free energy functional, okay? So it must be above these two. So it's if the free energy is here, your rounded object will be over here. And the point is, you know what is the difference between the lower bound and the thing you get after rounding. So it's like the true thing, which is this, my index finger over here, that's kind of in between these two. So you've kind of sandwiched it.
Okay.
So that's the
okay.
idea.
So Okay. So let me then reformulate the question the other way around. So with the rounding, you're guaranteed to have an energy that's higher than the free energy. So so you do always, with a full guarantee, sandwich the problem in that way.
Yep, exactly.
Okay. Very, very nice. So how come then, if we again focus on this two local Hamiltonian approach, how come the restriction to two local Hamiltonians actually helps with solving this problem?
So the two local, it does help for simplifying the calculation, but the main thing that helps here is actually the dense part. So that's the thing that really helps this particular rounding technique that we're using work here. Mm-hmm. And this rounding goes by something called correlation rounding in the classical computer science literature. So because you have these dense interactions, which means that you have like an interaction coupling almost every pair of particle, what you end up doing is you consider density matrices of over subsystems of some, say, m number of particles, where m is something smaller than n and greater than 2. So you choose all subsets of m particles out of n and keep density matrices over these m particles, while constraining that these density matrices be locally consistent. That is, if you have two different m size subsets of qubits and they contain their intersection is not zero, so they have some overlap, then if you're keeping two different density matrices on these two subsets, well, they must match up in the intersection. That's the kind of local consistency that we require for this relaxed optimization. Okay, so this is the kind of data structure that we are optimizing over. Now it turns out that if you have things like data structures like this, which correspond to keeping locally consistent density matrices on all possible subsystems up to a certain size, then something interesting happens. You can argue that if you were to now pick another subset of size that is less than m, or less than m minus 2 actually, or up to size m minus 2, randomly out of this out of all of your qubits, you sample it, then you do something called conditioning, which means you measure all of the particles in this subset, in this m minus 2 size subset. You measure them, you get some outcome, and then you try to figure out, okay, what is the density matrix on all of the on the other qubits. Now it turns out that if you condition on this random subset, then condition on this any two qubits that is not in this subset, they're kind of decoupled. So the high level idea is that if you condition on a random subset, then the other qubits that are not in this subset, they become pairwise uncorrelated. So this kinds of lets you build a rounding algorithm for this. And this is a property of this dense case. So for the dense case, you need to keep track of density matrices on all possible subsets up to a certain size. And if you have some kind of structure like this, they satisfy this property. That if you were to choose a random subset, condition on it, then other things not in the subset look loosely like uncorrelated. So
how come that's a condition of a dense matrix? So I would assume that if you have a constellation that's very similar, like if it's less dense, you would also have the same property. Am I missing something in that? Like, am I conceptually missing something in why this works?
Yeah, it's a bit counterintuitive, but you can think of it this way. So it's like you can have correlations only between certain number of particles. So if some particles are very strongly correlated, then other things might not be as strongly correlated. That's one of the loose ideas. And the other thing is like, maybe that's not such a great answer in this case. Let's try to formulate it slightly differently. So in this case, you have this dense system, which basically means that every particle is sort of interacting with every other. So it's like, in some sense, each particle is sort of loosely correlated with all the other ones. That's the basic idea. Okay. So now, if you condition on some number of the things it is coupled to, then condition on that, it looks like it's not correlated with all the other things. So this is kind of like the loose idea behind this dense systems. But I agree that it may not be very intuitive. You really have to
if you take a system that's less densely connected, maybe my intuition for a dense system is not correct, but like for a less densely coupled system, would you not have the same thing that you could consider a set that's correlated to, and then you would expect that anything for it, like anything external for that, would presumably not have an effect on that original qubit.
So for other things, something like a one-dimensional system, something like on a chain, you will have this kind of conditional decoupling, but that would be in a very specific order. So if you have like a 1D chain, you might condition on something, some patch in between, some segment in between, and then the ends that are left over, they will be decoupled. But the property of the dense thing is like you can choose basically any random subset, and with high probability, things that are not in the subset will be decoupled once you condition on what you have seen in this subset. So that's the property of this dense system, which is pretty interesting.
And that's also probabilistic then. I assume we don't have a firm bound there, but that it's a probabilistic selection.
It is indeed probabilistic.
Okay. And how does that now relate to bringing this back again to the optimization for this particular case?
So the optimization happens before you do this. The optimization just says run up some kind of convex program on these patches. Now in that there is a technical step, but to answer your question, this dense property is a property of the rounding algorithm. Now because you have this kind of conditional decoupling, your rounding algorithm now looks like something like this. You make your choice of this randomly sampled subset of qubits. So if you m with the size of density matrices you're tracking, you choose a random subset of size m minus 2. Now you imagine that you're measuring all the qubits in this small subset, and you see something. So you set those qubits to have that particular state. Okay. Now, given those qubits are in a particular state, recall this was like m minus 2 of them. Well, then you can assign like 2 qubit states to all the other things. Okay, all the other qubits that are not in this set. And it turns out, because they are now decoupled, you can assign the states of each of these qubits independently, and that's like the kind of the rounding argument. So you set your qubits in the subset to have a particular state depending on what the measurement outcomes were, and you can kind of figure this out theoretically, and condition on these. The other qubits are independent, so you can set them to be something based on what is the local state of that qubit after the conditioning. That's the kind of loose idea, and it's hard to explain without like looking at the equations. But this is the basic idea, that because you have this averaged out, randomly selected conditional independence, this lets you rebuild your density matrix by some small steps that you can iterate locally, which is that you can assign states on this small set, then you can assign states on each of these qubits kind of independently. And once you do this, you're guaranteed to have a state. It's not like you'll have a bunch of collection of patches of states which may not match up. This procedure guarantees that you'll have a state. And because you have this kind of decay of this conditional independence in an approximate sense, you can prove that the error you incur by doing this is small.
Okay. One thing that still confuses me a little bit with this patching is if we're now taking these, we're adding these independent subparts of our system, let's say. Are we saying that they would be the contributors of an increased energy, which ultimately brings is there an analogy between what we're doing now and a conceptual understanding for why the final energy of that system ends up being higher than, what the actual answer is, let's say?
You can repeat the question. I don't think I've quite followed the last part.
So after the convex optimization, we have some result that's not necessarily a state, if I understood it correctly, or not a well-formalized state. And then we apply this patching algorithm, which has the effect of turning this into a proper state. That part's fine. My follow-up question now has to do with the energy of these two states. Yeah. So we get some result. The energy of that, albeit a state or whatever it is lower than the actual free energy of the system. We're then doing a patching procedure where we instantiate qubits as if they were independent in, let's say, a probabilistic way. And somehow, through iterating over that procedure, we end up with a final energy that's above the correct answer and also the convex optimization answer. Is there some intuition? What part of this patching procedure brings in the additional energy? Like, why is the energy raised necessarily by applying this kind of procedure?
Right. So the thing is that your optimization is happening over these patches of states, not the full state. So the thing you're keeping track of while doing the optimization, that does not obey the properties that a full n-qubit quantum state should obey. And this lets you achieve something lower. So if you were to think of, let's say you have 3 qubits and you have some constraints coupling 2 of these, okay? So now you can minimize 2 of these constraints separately by minimizing over the 2 pairs of qubits, okay? And this would let you achieve something lower. But this may not necessarily be consistent with the 3 qubit state. So you can always locally minimize in general to something that is lower. So you can minimize each of these constraints separately, and this would give you a very low, let's say very low energy. But now if you try to impose the fact, well, this local thing I minimized must also somehow lead to a minimization of the third thing, well, then it becomes tricky, and then you might achieve something higher. So anything that is minimizing locally might not be the full global minimum.
Okay, so in the reconstruction, then you add back some additional constraints that you didn't have in the beginning, and they in turn ensure that the final energy of this needs to be higher than. I see. Okay, cool. When we do the original, let's say, deconstruction of the state, so before we apply this convex optimization algorithm, you said that we do it for subparts of the system. When we split that up, is that in and of itself the relaxation, and by considering those subparts, we per default end up in a situation where we can apply a convex optimization algorithm, or is there something more in the original pre-processing, let's say, or like alignment of this problem to a convex optimization problem?
So that is one of the main parts that you make a choice of what is the structure you're keeping, where you think, okay, I'm going to just keep something that looks like a density matrix on each of these small parts, and they must be locally consistent. So that's your choice of the one part of the relaxation. The other is choosing, in this case of thermal equilibrium, well, what is the thing you actually optimize? Because this free energy, this is like the minimum of an energy cost plus something called the entropy. Okay, so there's an additional entropy term, and this entropy, it is something that depends on the full quantum state. So if you instead just now have patches of the state, you cannot compute anything like the entropy. So we have to replace that term in the objective as well. So we replace this entropy with something that looks like a sum of the entropies of these small patches, roughly speaking. So instead of computing the full thing, you compute the entropy of each of these patches and you sum them up in some fashion.
Does that correspond to an assumption on the system? Like, is there a particular kind of system where if the constellation and this and that, you would actually get an overall entropy that's aligned with this?
That's a very good question. Maybe in other cases you would. Actually, in this case too, it's kind of like that. It's not, I would say, an assumption. It's a choice as to what is the thing you should keep for the entropy. And that choice, in our case, is dictated by this rounding procedure, where we had this conditional independence property and we are choosing this random subset and conditioning on that. So in this case, our choice of what we keep for the entropy is dictated by that. We keep something called a sum of conditional entropies. So it's like, so the idea is we choose a random subset C and compute entropy condition, the entropy of 2 other things, condition all that. And we keep like a sum of these entropies. And this turns out that if you were to if you were to apply the rounding procedure to a collection of local patches of states, local states, not quite the full state, and round to something, this particular entropy functional, this thing that we keep instead of the entropy, the sum of some things that look like entropies of the small patches, this quantity stays unchanged through this rounding procedure. So you're right that in some sense this is preserved, but it's preserved in the rounding procedure. Whether this will exactly correspond to the entropy of some actual quantum state, that's an interesting question. In this kind of setup for these densely connected Hamiltonians, it might, but it's not something we have looked at.
Okay. Okay, understood. So then moving on to the larger systems as well. So we go from a two-local Hamiltonian to a k-local Hamiltonian, and we try to find some computational estimates or like computational complexities for the equivalent algorithm. Could you describe why that becomes more problematic in this case now?
Right. So the two-local case, that's an efficient algorithm for an approximation. Now, in that case, we are able to take advantage of certain structural properties of the Hamiltonian. In the general case, for the general k-local case, without the dense assumption, that we don't know how that technique might carry over. Though certainly, we do have know of families of Hamiltonians where again you can have efficient algorithms to compute these free energies. So that's one part of the answer. The other thing is that we expect that for general Hamiltonians, general k-local Hamiltonians, and even general two-local Hamiltonians, without these denseness assumption or other equivalent assumptions, computing partition functions is actually very hard. It's harder than something called this computational class QMA, which is like the quantum analog of NP. So we know it is a hard problem. And our interest in this part of the paper is trying to kind of narrow down how hard it is. So QMA is just one quantum complexity class. There are many other analogs. There are many other computational complexity classes. And we kind of want to pin down how hard it is. And this is motivated by the fact that for the equivalent question, computing partition functions of classical statistical physical systems, something like just classical spins, we know how hard this problem is. We know how hard it is to exactly compute the partition function, and more importantly, we know that how hard it is to approximate it. And the approximation problem is we want to approximate this partition function to some multiplicative factor, and equivalently, we want to compute the free energy, which is the log of this, to some additive error. So that's the approximation version of the problem. And to reiterate, in the classical case, the computational complexity classification of that problem is very well understood. In the quantum case, we don't quite understand it. And part of our goal in this paper is try to pin that computational complexity down for quantum many-body systems, for quantum k-local Hamiltonians. And that's what we're doing in this section.
Mm-hmm. How do you approach that in general? Like, do you normally start an investigation like that numerically? Try to see, like, in some way how this scales with larger and larger systems, or is that simply an intractable, let's say, approach to even trying to figure this out? Do you have to do it analytically to begin with, or can you get some insights for, like, how to think about the correct approximations as you in a numerical way to begin with?
In this case, for this kind of abstract setup, I'm not sure like numerical ways are directly helpful for the question formulated. Though certainly, the expectation that this problem is hard is built from many decades of physicists trying to solve this kind of problem or related problems on computers, and seeing that in general this becomes quite intractable. In certain cases, again, you can take advantage of structure, but in general this is a very difficult computational problem. So the fact that you can try to address this problem, the computational complexity of this, is certainly motivated by decades of experience of physicists trying to do this problem numerically. But we didn't directly initiate our investigation numerically.
Mm-hmm. And so in the paper here as well, I think you referenced 3 other solutions here. That the QPF problem, which is then inherently related to the free energy. I take it that this is the, let's say, bulk of what needs to get done in that assessment for the general k-local case. Mm-hmm. Maybe you can just confirm whether that's true as well, so I'm not saying too much.
That is indeed correct. We show that these 3 problems that you highlight on the screen here, they are in a computational complexity sense, they're of equivalent difficulty. So if you could solve the QPF problem, you can solve any of these. If you can solve any of these, well, you can solve the QPF problem. That's the kind of idea behind these kind of so-called reductions.
Mm-hmm. And how do you formalize that, or how do you get to that kind of result? Like with these 3 other problems, is the starting point that you're trying to, let's say, transform the problem that you originally start with into one of the 3 categories?
Yeah, so I mean, there are, I guess, 2 separate aspects to the question. The first is, what is the motivation behind thinking of these reductions? So maybe I'll address that first, if you don't mind.
Yes.
Right. So we're interested in trying to understand, well, how difficult is it to approximate these QPF, or the free energy? Well, and we want to do some kind of classification of the problem in terms of known computational complexity classes or things we might come up with. But it turns out doing that kind of analysis is very hard. So what often computer scientists do is that you try to transform the problem into problems that are of equivalent difficulty. And that's the motivation for studying these. Can you find other problems that the problem you're trying to do reduces to? And do those problems reduce to the one you are trying to analyze? Because then, if you can now say something about the computational complexity of any of these problems, if you can say, okay, this problem is in this certain computational complexity class, well, then you can say that the QPF problem is also in that class. That's the idea. And how we came up with these particular families of problems, well, to some extent they were motivated by essentially what we expect in physics. As I told in the beginning, this partition function is something like a master key. If you can compute it, you can compute other properties. So if you want to compute something like a correlation between some number of particles, well, you can compute it by computing the partition function for certain slightly different parameters, and that's essentially the first part. And the partition function is also related to like your energy statistics. How is your system distributed in the different energy states you can occupy? So that relates to, well, what is something called the density of states? How many configurations are there in a certain range of the energy that it is allowed to have? Things like that. And that relates to the second point, this number of eigenstates. And the third one is a bit more different. It's not directly motivated by physics. In the third one, what we are doing, we are essentially relating this quantum partition function problem to something that is like an analog of approximate counting for quantum circuits. And maybe, let me see how I can explain it. So this approximate counting, this is again motivated by similar results in the classical computer science literature. It turns out that computing partition functions of classical statistical physical systems, that's basically equivalent to approximate counting of classical problems, classical constraint satisfaction problems. So these are the so-called NP problems, which are things whose solutions you can efficiently verify, but not necessarily find. Now you might ask the question, well, how many solutions there are to an NP complete problem? And computing that is, again, a hard question. But it turns out that computing that answer is formally equivalent to computing partition functions of classical spin systems. And again, and from that exactness, it follows that even the two approximation problems are equivalent. That if you can approximate the classical partition function, you can approximate the number of solutions to NP complete problems. And what we are doing here in this point 3 here is establishing a similar equivalence for the approximation of quantum partition function to a certain quantum approximate counting problem. So, and maybe I'll say one more line, and hopefully this won't confuse people too much. So QMA, this thing I mentioned earlier, is like the quantum analog of NP. These are the class of problems whose solutions you can efficiently verify on a quantum computer, but not necessarily find out, even with a quantum computer. Now we can ask, well, what is the number of solutions to a certain QMA problem? And this number is a little tricky to define, but let's just roll with number. And that turns out to be a very hard problem, this counting number of QMA witnesses or QMA solutions. And what we're showing here is that approximating this number of QMA witnesses is equivalent in computational complexity to approximating the partition function of these local Hamiltonians. And that is like the substance of number 3. And this is directly motivated by the fact that a similar equivalence holds in the case of classical systems. And that leads to powerful implications about the computational complexity of the classical partition function problem. And we show this equivalence hoping that we can now take this approximate quantum counting problem and maybe draw similar implications.
Okay, maybe that's a good segue to start closing the interview and talk about some of the next steps for the research. So we have these 3 problems now that we've been able to say that they're, well, up to a reduction, computationally equivalent to the problem that we're looking to solve. In terms of moving forward with this research, or with any of the other 3 problems for that matter, do you see any ways that, like, given the research that you conducted now, you might be able to take this to the next level, let's say, or just one further step along the direction of figuring this out?
Right. Yeah, that's a really interesting question, and we have been working on it. We recently put out another paper which tries to build upon this and show. So I talked about this quantum approximate counting problem, and in this more recent paper, we show that a certain problem that arises from some mathematical objects in group theory and representation theory, counting that or approximating that turns out to be basically reduces to a problem of quantum approximate counting. So one step, so maybe to step back a bit, one thing that is a next step is to try to find more problems that are equivalent in this computer science sense. So here we have two problems that are kind of inspired by physics and one inspired by quantum circuits. Are there other families of these equivalent problems? And we kind of give an indication that this particular problem we talked about in this recent paper, something about computing so-called Kronecker coefficients, that's in some sense captured by this quantum approximate counting. But are there more problems like this? That would be interesting to know. And then the other thing we don't quite answer is, can we say something about, like, what is the computational complexity class that captures the difficulty of this approximation problem? And can you separate it from other known complexity classes? We didn't quite address it in this paper, but that's certainly an interesting question and presumably a very difficult one. But it'd be good to try to make some progress on that front. And
is
the
there
other
a way
part,
to make is there a way to make incremental process on something like that, or is it? To me, it feels like either you get it, like either you find some way of approximating at least, like, maybe not the optimal bound for the computational complexity, but at least a bound for computational complexity, or you don't. Is there some form of middle ground, or is it either or? So
the incremental part is trying to find other equivalent problems. And then one of these problems you might be able to understand better the computational complexity of. And so that's something that would be the next, that is basically like the work going in. The other things people might do is they think about something called oracle separations, which is establishing separations in unconditional separations in computation complexity is often tricky, but you can often do separations relative to some kind of oracle. Suppose you had the ability to solve this particular problem and the ability to make some get answers from something like an NP oracle or some other oracle. So it just solves some problem which you don't know how to do, but it might just do it. Well, relative to that, do these classes separate? And that's often like a first step that people do to proceed towards unconditional separations. So things like that are something people might certainly do.
Okay, understood. From your perspective, I don't know if you have any more points that you would like to raise, but if you don't have that, my final question to you would be whether or not, like, to the wider research community of people that are interested in this, whether you have any requests or like anything you would like to see in terms of research from the wider community going forward.
So in terms of like future work, the other part, aside from these reductions, is the part we talked about earlier, which is this relaxed optimization. I find that to be a very interesting technique, and there's now an increasing number of people who are more interested in applying this relaxation ideas to many body physics problems, and it would be cool to see more progress on that front. And that's something I'm trying to think about, and it would be just more fun to have more people there. So that's something. That's one thing that immediately comes to mind.
Okay, great. But then, Anirban, let's close it here. Thanks a lot for joining.
Thank you so much for doing this, and yeah, great.